So let's try an example of calculating execution time. In this case, effective CPI is provided. So we have NVIDIA, 1 gigahertz, and a GPU is executing this 3D rendering program, and it has an instruction count of 1 million instructions. Checking the data sheet, which is typically how we approach these problems. This information is in a data sheet. You can find the effective CPI to be 7.0. How long does the GPU require to render graphics using this program? We're going to use the CPU performance equation. You should know this equation. You can memorize it if you like, but I'd rather this make sense to you and you can derive it. We have the execution time is the instruction count times CPI times the cycle time. IC times CPI times cycle time. So in this case, the frequency is given as 1 gigahertz. Excuse me. How many nanoseconds does one instruction take? Well, it depends on the CPI and it depends on the clock cycle time. First question, what's the clock cycle time? At 1 gigahertz, the clock cycle time must be 1 nanosecond. So we have 1 nanosecond is the clock cycle time. The CPI, well, that's nice. It's given in the 7 in the question. And how many instructions? Well, it's given to 1 million. So we're going to plug and chug in this case, and we get 7 times 10 to the minus 3. This is times 10 to the 6. This is times 10 to the minus 9, 10 to the minus 3. We recognize 10 to the minus 3 is a milli prefix. Units are seconds. This is 7 milliseconds to execute this program with these parameters on this hardware. Change the application from graphics rendering, let's say, to motion detection. You're going to have a different execution time. Why? Because the instruction mix is different. What did you change? You didn't change the hardware. You didn't change the NVIDIA processor. You didn't change the frequency in that case, but what did you do? You changed the instruction count by changing the algorithm. If I look at a different processor, I'm going to change the number of clocks per instruction. Or if I boost up the frequency by changing the multiplier of the clock, as we learned today, you can also make it faster by changing the electrical engineering aspects of the underlying switching rate. Excuse me. Let's try another example. Here we have a 40% arithmetic instruction mix with 5 clock cycles per arithmetic instruction, 30% branch, 30% data transfer with 12. Data transfer very long because we're accessing slow memory. We have 20,000 instructions in total, and it's running on a 3 gigahertz CPU. Find the instruction time of the program. Again, we're going to use processor performance equation, instruction count, times CPI, times cycle time. You need to know that for sure. It's on the next quiz and the next exam for sure. Instruction count times CPI times cycle time always gives you the execution time of the program. These are weighted values. We can use the proportionality equation that we had. We derived it here to look at calculating the, we have an equation. Let's see. Here we go. The weighted value for CPI. Give me 1 second. We're going a little bit back. Here we go. Effective CPI is the CPI of each instruction times its proportion, and we sum those up. So this example is putting that into practice. So 40% take 5, 30% take 2 clocks, 30% take 12 clocks, on average 6.2 clocks. The clock rate is 3 gigahertz, therefore the period is 1 over 3 gigahertz is 333 pico, which is 1/3 times 1e minus 9 seconds. We have 20,000 instructions in total, 6.2 clocks per instruction, and 333 pico. We end up with 4.1 e minus 5. If I want to get this into standard units, Latin prefixes to power of -3, -6, -9. The closest one is -6. This would be 41.3 microseconds. We write microseconds with a Greek mu. This is very important to know. Greek mu is micro. You guys know that from physics. But sometimes on the keyboard, we don't have access to Greek characters, so we write U, the lowercase letter U. Meaning micro. Okay. A lot of times when we write M, M is going to always mean milli. Okay. What about capital M? Okay. This is lowercase m. This is capital M. This is mega. Okay. And I try to use a capital letter for that. Megabytes, megabits per second if it's a data transfer. This is milli for milliseconds. The lowercase letter u is for micro. Please know the difference. It's very important. It's going to come up on exams. It's going to come up on data sheets. It's going to come up on emails. Sometimes you don't have access to the Greek alphabet to write the letter mu. And someone writes something like this, u seconds. That is microseconds. If somebody writes 3 milliseconds, that's 3 milliseconds, not 3 microseconds. It's not 3 microseconds in an email. That's a little tip. So let's try putting all these things together in a composite example. The question is, what is the effective CPI for the baseline design as originally given? What we're going to do is calculate the baseline, and then we're going to try some selective improvements, either improving the arithmetic logic unit, which is really the heart of the processor that crunches the bits, or we can improve the memory system, right? Add more memory to your processor, or faster memory, or faster front side bus. What's the influence on the execution time, which is probably what the customer cares about most, or you as a user, you want your response time to be fast on your machine. Or we can improve the branch, which is a control instruction. So first, let's start with calculating for the baseline. How do we do this? This is, again, using proportionality constants. We're going to multiply each of these and sum them up. So you can see that the average CPI is 2.2, same as the previous example. Now, what comes next? Well, as project lead, you're considering some alternatives to make this program run faster. And you're going to be improving different aspects of the execution. So alternative number one, how much faster would the machine be to execute this program if a better data cache reduced the average load time to 2 cycles? So the question is, how does this enhancement affect the CPI or change the effective CPI? Well, we're only changing what? A better data cache is reducing the load time to 2 cycles. So it used to take 5, we're going to reduce it to 2, the rest of these remain the same. What's the effect on the overall execution time? We're not changing the instruction count, right? It's a key thing to know here. Instruction count is the same. Instruction count remains the same in alternative 1. What about the frequency? The frequency is going to remain the same. Why? We're not changing this architecture. We're not going from MIPS to Intel, so the instruction count is going to be the same. We're not changing the compiler. We didn't mention that. If we do, we have to tell you in the problem. The frequency, we didn't mention anything about making the clock rate faster. That's the same. What does change in this problem? The effective CPI changes. So let's calculate that. These are the same, but you can see here this goes from 1.0 to 0.4 is the effective. All right, contribution of load to the overall CPI. So we went from 2.2 down to 1.6. You see, we doubled, more than doubled, the rate at which we do load, which means less than half the time. But the effect goes from 2.2 to 1.6. Why? Because the proportion of load was only 20%. So if someone asks you how much faster, we're not changing instruction count. We're not changing frequency. So that means we don't change the clock cycle time. That's the clock period. The only thing changed, really, we went from what? From 2.2 CPI down to 1.6. So it's the ratio of the CPIs is actually telling you the ratio of execution times. Why? Because we have performance equation. Let's go back. Performance equation. Instruction count times CPI times clock cycle time. If I'm doing the ratio of different executions, and I leave this the same and leave this the same, I just change CPI, it's the ratio of CPI is going to tell you the ratio of execution times. Everything else remains constant. They cancel out for a ratio. So that's what we see happening here. So this is very cool to me. Without actually running this program, I can tell you if you make this change, it will be 37.5% faster. That's amazing. This is very important before you would say embrace this design change to have some estimate of the impact. Using the CPU performance equation and breaking this down into instruction count, CPI, and clock cycle time allows you to kind of partition between electrical engineering, computer science, computer engineering aspects to see the trade-offs. Next one, let's compare using branch prediction to reduce a cycle off the branch time. So the same thing is going to happen here. We're going to reduce branch, right, from 2 to 1. So now it's 0.2 times 2 is 0.2. So the ratio of CPIs in this case is 2.2 divided by 2.0 is 10% faster. Alternative 3. This is where it starts to get interesting, leading us up to using multiple cores and multiple execution units. Suppose I have 2 ALUs rather than 1, and I can execute 2 instructions of arithmetic logic type at least per unit time. So what does that do? It reduces the effective clocks from 1 down to 1/2. So in this case, 1/2 times 1/2 is 1/4. Used to take 1 clock per instruction, but now I can execute 2 ALU instructions per unit time. That means that the effective CPI is half. So we see that happening here. We went from 0.5 down to 0.25, and this is the new effective CPI for the entire workload under alternative 3. So the question comes, well, what's better? Well, we always want to think about cost. Suppose the cost was equal. Which design alternative do you recommend? Well, obviously we're going to pick the faster one if everything else is equal. And in this case, we can find this alternative to be better. So let's look at making the clock rate faster is changing the electrical engineering aspect. Suppose you have 2 processor clock cycle times. One period, in this case, is 1 nanosecond. Another is 1/5 of a nanosecond, 0.2 nanoseconds. That's 200 picoseconds. But there's some trade-offs. When we reduce from 1 nanosecond down to 0.2 nanoseconds for the clock cycle time, it actually takes more cycles. You're going to say, well, why did that occur? Well, the hardware may require certain adaptations to work with that very fast clock. And let's get a graphic to depict this. There's some trade-off between these sometimes. We have to look at both together to find the real influence on execution time. So here we have a processor which is very powerful. It's large. It can execute 1 gigahertz clock rate, and it took 4 steps in this case to execute the entire workload. 5 gigahertz processor is very fast. It's very nimble. That could be an advantage too, but it takes more steps to execute the same workload. So you can see that they actually get there in the same time. This is slower but powerful steps. This processor with a high clock rate is rapid but simple steps. Ideally, we'd like both. We'd like a high clock rate and very powerful processors. We try to attain both, but sometimes there's a trade-off. We can't obtain both all the time. In this case, we both execute, in this case, either 1 gigahertz or 2, both execute in 4 nanoseconds because we have 4 steps at 1 nano, and this is 20 steps at 5 giga because there's 5 cycles per step, and this way is going to take 20 clock cycles. So for a given CPU, as I mentioned, this different clock rates does not necessarily imply it's faster. If the instruction set architecture is the same, you're in a pretty good shape. But if these are different instruction set architectures, one's more powerful than the other, you have to look at the product of these two using the CPU performance equation. So for a given clock rate or a given CPU, increasing the clock rate does increase performance as long as the system does not become imbalanced, and we'll talk about that later. If memory is a bottleneck, it doesn't matter how fast you make the processor if you're waiting for memory all the time and the processor execution stalls when memory executes. We can take a look now at this video for AMD frequency record, which is pretty cool, and doing some supercooling to get the maximum clock rate for a given instruction set architecture.
With us, we have among the most respected overclockers in the AMD community. What we're trying to do is see what we can do with AMD FX. And the question is just how far can we go?
So we're not running any benchmarks, we're just shooting for the highest CPU Z. So we boot up from the BIOS with pretty safe, easy settings, and then we'll adjust the frequencies on the fly. Just seeing how the frequency scales, going from air, water, phase to extreme. So we're just going up little by little, 7 gigahertz so far, no problem.
These days we've kind of stepped it up a bit. When we run liquid nitrogen, it's kind of a preliminary test for us, and it's been overclocking for the rest of the world for a long time.
7873, getting closer to the 8 gigahertz. 8 gigahertz. When we switch over to helium, the base temperature has usually been between negative 220 and 230. 8.335 megahertz. That was the highest CPU frequency ever. And we had the virus scanner enabled. Let's see if we can go higher. So this would be 8420 if we can make it. 8429.
Congratulations, everyone. That is awesome.
So let's try an example, putting all these elements together to show that clock frequency by itself is not a complete indicator of CPU's performance. If your customer wants to execute something quicker, clock frequency is important, but it's not the whole story. So here we have a signal convolution task. If you are a digital signal processing electrical engineer, each iteration of the convolution algorithm requires 1,000 instructions. That's probably pretty realistic. On both Intel and AMD devices, this Core i3 from Intel has a 1 gigahertz clock, and this AMD FX model has a 2 gigahertz clock. Because we have a faster clock rate doesn't mean that this is going to be faster. Well, we have to look at also the CPI and also the instruction count. We know the instruction count's the same. That's nice. But look at the CPI. The CPI more than doubled when we doubled the clock rate. So if we double the clock rate, we're going to half the clock cycle time, but we more than doubled the number of clocks required per instruction, which means we're going to have more than that number of clocks, double in this case, to execute the entire program. So let's use a CPU performance equation. We substitute in and we end up with 4 microseconds because you had 1,000 times 4 times 1 nanosecond per instruction of this is a clock cycle, right? We have 4 instructions, 4 clocks in this case per instruction. End up with 4 microseconds, and you had 1,000 instructions, 10 clocks for every instruction, and here we had 2 gigahertz corresponds to half a nanosecond. Half a nanosecond is 500 picoseconds. That's 5 microseconds to execute on the AMD. So even though the AMD has a faster clock rate, it may be a longer execution time. You're going to say, well, yeah, this is a very isolated example, and you just change this ratio, and therefore it works this way. But this is very practical. Suppose you're even buying a laptop computer, and you're looking at the clock rate. Getting a faster clock rate may not be as cost effective as adding more cache. Because as we saw, things like load and store operations, which are data transfer instructions, typically have the most clocks per instruction. If you can add cache and reduce that execution time for those instruction classes, it's very effective, cost effective, to increasing the throughput or decreasing execution time. Core i3 in this case providing higher performance for the task despite its lower clock rate.
Here's an equation for MIPS. It's something we're already familiar with. We talked about instruction count. So if you take the instruction count and scale it to the number of millions of instructions per second, using this equation, you get the MIPS rating. So here's a little source of naming confusion. We have the MIPS processor and we have the MIPS metric. So you have to get it from context. So if someone talks about how many MIPS is this processor, it's talking about this metric and the value for this metric. If it's talking about the MIPS instruction set, it's talking about a brand name, which is MIPS. So we'll try some examples here and look at this number. Again, MIPS is based on instructions per unit time. It's a throughput metric. It's a throughput metric, not a time metric, a throughput metric. But it's not completely indicative of CPU performance. Why? Different instructions do different things, right? Some instructions are very simple. Some are more complex. Multiplying two numbers is a higher complexity operation than adding two numbers. So you're talking about the number of instructions per second or millions of instructions per second. We need to keep in mind that that's just a number of how many instructions got done, but not what type of instruction. Remember we had CPI, which is talking about the number of clocks per instruction. That's the time complexity of each instruction. How many clock cycles does it take? Here we're just counting instructions no matter what type. Okay? So you're going to say, well, how useful is that? Sometimes it is useful, especially if it's the same instruction set architecture. If you have the same ISA and they have two different MIPS ratings, you can compare them very directly because we know they have the same type of instruction set. If I use the same compiler and the same optimization level with the two processors, it's giving me a very direct comparison on performance. So here is our calculation. Again, this is just writing it as an equation. Instruction count divided by execution time is instructions per time or instructions per second. This is giving us the millions. There's also flops. Okay, well, what's a flop? Flop is a floating point operation per second, so it's a particular type of instruction. Floating point operations are for mathematics when we're using non-integer values. And this is usually used in scientific computing or anytime we're doing complex calculations. So if you want to see some examples of these, okay, you can go here to this website, the top 500 lists supercomputer. So here, top 500, they keep this updated every month or so. And what's the number one supercomputer in the world? I just reviewed a paper for a guy that works at a supercomputer center in China, which is actually number one right now. But they have, current list, they have new articles and things. If you're interested in this area, supercomputing, it's basically using hundreds of thousands of cores to do high performance computing. And they changed their website, making it more convenient. Let's see here. I cannot get to the list. Okay, here's our list. So this supercomputer in National Supercomputer Center in China is number one. It's been on the top for several years. 3 million cores. Okay, so obviously it's not one chip, but they'll have quad-core, octa-core processors, and they have a gigantic warehouse full of these, right? So we see some of the throughput ratings here. What's this? Teraflops, right? So what's a floating point operation? That's adding or multiplying two floating point numbers. This is how many trillions of those per second. This is 33,000 trillion. Yeah, that's a lot. About power consumption of that supercomputer. What units is this? 17 what? 17 megawatts. This is 17,000 kilo. That's like all right, amazing, right? So we talk about energy. It's a real area of hiring, minimizing energy. We have a lot of ways to do that. We just start you out in that class, in this class. But you can see here, Oak Ridge National Lab, even though they have fewer cores, they have a lot of optimizations in the memory hierarchy, which we know is a good way to improve performance, and we'll talk more about that in a later module. But this makes some of these values real, okay, and you can take a look at these. So you're going to say, well, how do I do a calculation with these? Maybe if you, usually you're given some benchmark, and it says it has this many floating point operations, and you get the execution time, you can compute the number of megaflops, millions of floating point operations per second. In this case, teraflops, right? It could be megaflops, gigaflops, or teraflops. So this is a summary slide for Module 4. Module 4 is our last module for the exam. We can see here everything on one page that is a summary of these different types of relations and equations and metrics that we use. And these are all things you should know for the exam. So to recap on these, we had a few different metrics. Some were time-oriented, some were throughput-oriented metrics. Time-oriented metrics, the way I understand these or remember these, response time is what the user sees. Execution time is another word for processor time in isolation, which is one subterm, right, of response time. There's a thing called latency. Latency is a time measure, but it's a measure of delay. Latency is a bad thing. We want to minimize latency. Execution time we want to minimize as well, but that's getting work done at least, right? And what's throughput? Throughput is output per unit time. So what are some of our metrics for throughput? We had flops, MIPS, multiply accumulates per second were some that we covered. Execution time, we talked about relative performance. We said it's the inverse of the execution times for a CPU relative performance. Then we got into measuring clocks. We said clocks were the intrinsic unit of time. Okay, clocks, so time clocks. Intrinsic unit of time for a processor. And I said it's like electron volts. Why did I say that? Anyone who was awake last week?
Because electrons so small.
Yeah, because if you're working in physics, right, and I gave you the story, it's a true story. I went to the physics professor and the homework was atomic level and I was using joules for all the calculations, which is totally valid, but it had the whole page full of numbers and it's hard to keep track. But sometimes he said, why don't you work with the native units? You're just working with a few atoms here. You don't need joules, just work with electron volts. It's another measure of energy, but it's the intrinsic element, right? So when would we use clocks? Sometimes we want to calculate time in terms of clocks. Here's a simple example. I thought of this to prepare for class today just to show you guys. All right, we had this example we can use as a run example. I think it's actually after this. I give a little program fragment and we talked about static versus dynamic instruction count. Yeah, we're getting closer. Right? Clock cycles. Yeah, I went too far back, sorry. Right here, here you go. So here would be a great example where it's easy to work with the intrinsic units of clocks rather than nanoseconds. All right, if you have a table, which you may give you a table that says set instruction, any memory access instruction takes, I don't know, 2 nanoseconds, or we can equate that to clocks if I have the clock rate, right? You can add up and work with fractions of a second times 10 to the minus 9 and add these all up, or you can just add up how many clock cycles each one takes, if that's what's given in the table, get the total number of clocks for the program, and then just convert to seconds once. So if someone wants you to find the execution time for a program, sometimes it's easier to work with clocks rather than seconds, even though they're measures of time. One unit is tailored to that domain. And the domain of CPUs, just like when you're working with atomic scale energy calculation, you may want to use electron volts. Here we may want to use clocks, and you can see that it's a lot simpler to work with 15,000 as a number than sometimes 10 to the minus 8 or 9 or 7 or whatever the answer is coming out. There's still units of time. So I want you to understand a clock rate and clock frequency, two words for the same thing. Clock period, which is the duration of the clock cycle time. Okay, last one. Oh, it's giving me a hard time. Okay. As units of time. So all these equations actually are the same mathematical relationship. They're the same physical relationship. We're changing the units, and this is providing us a proportionality constant. That's literally what CPI is. CPI is clocks per instruction. It's relating the number of clocks that instruction takes. Well, each instruction class or each instruction itself takes a different number of clocks depending on what the instruction is. Makes sense? So we can calculate the effective CPI as a weighted average of the individual CPIs. What does that mean? Well, we have some proportion is data transfer. How long does data transfer take? Well, that's its CPI sub I times the proportion we have is for this workload, its effective CPI. And we talked today about instruction rates. So I'll let you guys ask any questions on Module 4. And then we can talk about material. Yeah, good.
So latency is its own thing, right? It's not part of response time?
Latency is its own thing. Latency can be the same as network time. We can have different types of latency. We can have network latency, which is usually where it comes into play, but we can also have latency in transmission between the processor and memory over the address bus and data bus. Other question? It's a good question. Latency is its own thing, but a lot of times where we see latency is a network latency.